Hi guys, welcome back to Calculus with Mr. Robeson. All right, so today we're going to look at one of what I think is the most fun topics in AP Calculus. It's called related rates. It is a little difficult because all of them are word problems, but they are always interesting and fun to solve. So everything is changing with time. We're going to look at the steps to solve related rates questions, and then we're just going to look through examples. The second video will also just be examples and more practice. All right, so when we're working with related rates, everything is changing with respect to time. All right, so everything is going to have a d, whatever variable we're working with, over dt. So we're no longer using dy dx because we're not taking derivative of y with respect to x. X is no longer our variable. Our variable is time. The problem is not everything is going to have a t. All right, so for instance, this y here is some function of time. This x here is some other function of time. All right, so there's this other variable t that we're not seeing. So if we take the derivative of this guy, derivative of y is going to be dy dt, not dx, dt. All right, derivative of x squared is going to be 2x times derivative of x, which is dx dt. And derivative of 5 is 0, so 5 is not a variable. It just goes away. So that's going to be our answer there. All right, so it's a little different than before. So now when we're taking derivative of x, remember, everything is a chain rule. All right, I just keep saying this. I don't know if we always remember what that means, but everything is a chain rule. So anytime we take the derivative of a variable, we have to put a d whatever dt for that variable. All right, so here, this is the area formula for a circle. Area equals pi r squared. All right, so the rate of change with the area with respect to time is equal to pi is a constant. So we just leave it out there. So we bring down the 2, we get 2 pi r to the first now times derivative of r. Well, r is changing with respect to time as well, so it's dr dt. All right, here we have area equals length times width, the area of a rectangle. So dA dt is the derivative of a equals, now both of these are functions of time, of t. So when we take the derivative, it's a product rule. So it's first, I'm going to use the cursive L, times derivative of the second, dw dt, plus the second, w, times derivative of the first, dl dt. And I always use the cursive L so it doesn't look like a 1. All right, so here again, volume equals pi r squared times h. This is the volume of a cylinder. R is a function of time, h is a function of time, pi is a constant, v is a function of time. So when we take the derivative, we get dv dt equals, now we got some choices. I'm going to actually group the pi with the r squared and say that this is my first term, and then the h is the second. So it's first, which is just pi r squared, times derivative of h. H is changing with respect to time, so its derivative is dh dt, plus the second, h, times derivative of the first. So the pi stays, we bring down the 2. It's going to be the same thing as this guy up here. We're going to get 2 pi r times dr dt, just like that. All right, so now when we're working with problems, we're doing actual word problems, like this dA dt might be what we're finding, or dr dt might be what we're finding, but they'll give us these rates of change, and they'll give us the r here, or they'll give us the length and the width, and like one of the sides is changing, or how fast both the sides are changing, because this is what this is. This is a rate of change of the width, this is a rate of change of the length, this is a rate of change of the height, down here is a rate of change of the radius, this is a rate of change of the volume. And they were all going to have units. So be careful when we're working with units here. All right, so here are our steps to solve related rate problems. So first thing is we're going to read through the problem, and we're going to list what is given. Just write down what's given. Maybe you can underline it in the word problem. Just list what's given. Next, we are going to draw a picture, a graph, a sketch, whatever, and then we're going to label whatever we can on there. Next, we're going to try and come up with some sort of an equation. So write an equation involving the variables whose rates of change either are given or are to be determined. All right, so this will usually be some sort of area or volume formula or the Pythagorean theorem or a trig function ratio, something along those lines. we'll make an equation that involves the sides or the things that we are using. After that, after we get the equation, we take its derivative, right, using the chain rule. So we're doing it implicitly. Everything is with respect to time. So everything is going to get a d whatever dt. After that, we're going to try and plug in as much as we can. So once we wrote down the givens in the beginning, we should be able to plug a lot of those things in. Right? You may need to do some other information. So step 6, sometimes you have to do it, sometimes you won't. Sometimes you have to do some extra work. Sometimes you have to plug back into like the original equation to get a missing side or something like that. And then you should be able to solve. All right? And don't forget units. You could lose points on your AP exam from leaving off units here, guys. So don't do that. It's a really easy thing to remember. All right, so our first example. Water is drained out of a canonical tank. So that means it's a cone. Canonical means cone. The volume, the radius, and the height of the water level are all functions of time. Here is our volume formula for a cone. So volume equals pi over 3, or 1/3, r squared times the height. Suppose that the height is changing at a rate of negative 0.2 feet per minute. All right, so that was the height. The radius is changing at a rate of negative 0.1 feet per minute. What is the rate of change in the volume? So we want to know the rate of change in the volume when the radius is 1 foot and the height is 2 feet. All right, so I underlined my givens here, but I'm going to go ahead and write them again. So we got r equals 1, and that is foot. We've got h equals 2, and that is also feet. We've got a rate of change in the radius, so that is dr dt. It is negative 0.1 feet per minute, which makes sense. If the water's draining out, this radius here is smaller than the radius was up here to start, which would go all the way across there. All right, so the radius is shrinking. The height is also going to be shrinking because it's getting smaller and smaller as we go down. So here's our height straight down from there. Very straight, right? I know. All right, so they give us that. The rate of change in the height is negative 0.2 feet per minute. All right, and I think that's just about everything they've given us. All right, so there's our givens. We've got a graph. They gave us a graph. So nice of them. Equation. They gave us an equation. Here's our equation right here. So now we need to take the derivative of that equation. So I'm going to write that equation down here so I can take its derivative. So we get pi over 3 r squared times h. So I'm going to do a product rule with that being the first and that being the second. So the derivative of the volume. Volume is changing with respect to time. So we get dv dt. That's actually what we're trying to find. Find the rate of change in the volume. Often I'll write that down too. We want dv dt. All right. So dv dt equals first pi over 3 r squared times the derivative of the second, dh dt, plus the second, h, times the derivative of the first. So pi over 3 is going to stay. We bring down the 2, so that'll give us 2 pi over 3 r to the first times dr dt. Now the whole reason we took this derivative is because they gave us rates of change, and if we take the derivative, we get rates of change, and we were trying to find a rate of change. So that's the only way we can get to rates of change is by taking the derivative of this function, this volume function here. So now we're trying to find dv dt. We've got r, they gave it to us. We got dh dt, they gave that. We've got h, we've got r, we've got dr dt. So if we just plug in everything we know, we'll be able to solve for dv dt. All right, so now we took our derivative. Now we're going to plug in. We don't have any extra work here, and we're just going to be able to solve. So dv dt equals pi over 3 times r squared, which is 1, times dh dt, which is negative 0.2, plus h, which is 2, times 2 pi over 3, times r, which is 1, times dr dt, which is negative 0.1. And now we're just working all this out. So if we just type that into the calculator, we get that dv dt equals, all right, so this guy's going to be negative, this guy's going to be negative, so our answer should be negative. So I did get a negative number, 0.6283, and it kept going. Now we need units. So it's volume. We were working in feet for the side lengths. So that means the volume is going to be feet to the third. Volume is always going to be units to the third. Area will be units squared. Lengths will just be the units. Per, and these were both per minute. So this is per minute as well. And there's our answer. So the volume is decreasing at 0.6283 cubic feet per minute. So you could also say decreasing instead of negative. That would be fine too. All right, let's take a look at another example. Ripples in a pond. So a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. So we have circles here. So this is a circle. As shown in the figure, the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So this was the radius increasing 1 foot per second. When the radius is 4 feet, at what rate is the total area, A, of the distributed water changing? So I'm drawing my picture here. Here's my radius. All right, so our givens. So we were given that our radius at this exact moment that we're looking at is going to be 4 feet, and that the radius is increasing at a linear rate of 1 foot per second. And let's see, we want to find the rate of change in the area, dA dt. So we've got our givens, we've got our graph. We need to make an equation. Well, we're talking about the area of a circle. So the equation that we want is area equals pi r squared. All right, that's the area formula of a circle. We are supposed to know area formulas. We don't have to know volume formulas, just FYI. So there's our equation. Next, we want to take its derivative. So A is changing with respect to time. That gives us our dA dt. We bring down our 2. We get 2 pi r times dr dt. The keen-eyed ones of you will notice that this is the formula for circumference right here. All right, so now we want dA dt. We've got r. We've got dr dt. We can just plug in. So our next step is to plug in. So we get that dA dt, the rate of change of the area with respect to time, is 2 pi times r, which is 4 times 1. So that looks like 8 pi. We need units. Our r was in feet. Our dr dt was in feet per second. So feet times feet per second gives us feet squared per second, which makes sense. Feet squared is an area per second. That is our time. There was no extra work on this one either. Getting off easy so far. All right, another one. Air is being pumped into a spherical balloon. So we're working with a sphere, it looks like, at a rate of 4.5 cubic feet per minute. That is a rate of change in the volume since it's cubic feet. So dV dt, change in the volume, is 4.5 cubic feet per minute. Find the rate of change of the radius. So we want dr dt when the radius is 2. So when r equals 2. So we need to have the volume formula for a sphere. Usually they'll give this to you. But volume for a sphere is 4/3 pi r to the third. All right, so I guess we can take one of those and make a graph if we want, or I can just draw a little picture here. Here's a sphere. Here's our radius. I suppose I should make it a sphere instead of just a ball, or instead of just a circle. So there, now it's a sphere. Beautiful, right? I know, I'm an artiste. So we've got givens all written down. We got a graph. We got an equation. Our graph here is our picture, by the way. Now we need to take the derivative. So here's the formula for volume, where we're dealing with the rate of change in volume and the rate of change of the radius. So we take the derivative. That gives us dV dt equals, bring down the 3. The 3 is going to cancel out. We get 4 pi r squared times dr dt. The keen-eyed among you will note that this is just the formula for surface area for a sphere. All right, but now we can plug in. All right, we've got dV dt. We've got radius at this moment, and we're trying to find dr dt. So we can plug in, and we're going to be able to solve for this. So we go to our next step. We took a derivative. Now we're going to plug in. So dV dt equals 4.5. We get 4 pi times r squared. So that's going to be 4. 2 squared is 4 times dr dt. So we're just going to divide here. We get 4.5 divided by 16 pi. It's the rate of change in the radius per time. We had 2 feet here, or sorry, feet squared here, feet cubed here. So we're going to get feet per second, because this was per second. No, we're minutes in this one. Second was the last problem. Per minute equals the rate of change in the radius dr dt. There we go. You can simplify that, change it into a decimal if you want, but you leaving it like that's also fine, as long as you have the right units and the right numbers. All right, so that was how related rates work, and we did a couple basic related rate problems. The next video we'll tackle some more related rate problems. So I'll see you again soon.